This video is going to cover clustering, and this is for the graduate level representation learning class 791. A typical supervised learning problem has both data and labels, and data is usually represented by X and labels are represented by Y. Unsupervised learning only has the data. So this just may mean that the algorithm only has access to data and has no need for the labels, or it may mean you don't even have the labels. So it totally depends, but you can use an unsupervised learning algorithm on labeled data. You're just not going to use the labels. The first clustering algorithm that we're going to cover is k-means. This is a pretty standard algorithm that a lot of people use today for many different applications. What we want to do is get k clusters, and we're going to describe each cluster by its mean. This is an iterative algorithm. It's very simple, and it actually works pretty well. Here are the steps. We're going to initialize the cluster centers randomly. We're going to compute the distance from each point to each cluster center, and then we're going to assign each point to a cluster using the minimum distance. And then we're going to take these clusters that we've created and recompute the cluster centers based on the clustering that we have. And then we're going to repeat steps 2 through 4 until our algorithm converges. We are going to set k, we the programmer. So this is going to be a hyperparameter. The cluster centers are going to be represented by this mu. There's going to be k mu's or means. We're going to use Euclidean distance as our distance measure, which is the same as the L2 norm. And we're going to calculate the distance between each point and each cluster center. So where each point is going to be xn for all xn, and then all the cluster centers are going to be the mu i's from 1 to k. Then we're going to assign each point to a cluster using the minimum distance. So we're going to compare this xn. Right here, we're going to compare this xn to every cluster center, and then we're going to say, okay, assign it to the cluster with the minimum distance. Then we have all of these clusters, C1 through CK, and each cluster is a set of points. We're going to take each set of points, and we're going to compute the average, or the mean, and that will be our new cluster center. And then we're just going to repeat steps 2 through 4 until convergence. So the points will move around between clusters, and eventually the points will stop moving. And once the cluster centers stay the same, it has converged. So here's the algorithm in a more formal format. We have the result is k cluster centers, right? We initialize mu1 through mu k randomly. Usually what you'll do is you'll select a point in the data set. So you'll just select k points and start with those as your cluster centers. And then while you haven't converged, you're gonna, for each point in the data set, you're gonna calculate the distance from that point to each cluster center. And then once you've done that, you're gonna choose the minimum distance and add that point to that cluster. So D here, DI is just sort of a temporary variable that's keeping track of our distances, so we can choose the minimum. And argmin tells us which cluster to add the point to. So it finds the argument of D, right, or the index of D that has the minimum value. And the union here is just saying, okay, we start with empty clusters and we add points to them. And this for loop just goes back through and recalculates the cluster centers. So it goes back through all k clusters and calculates the new cluster center for those clusters. Let's run through an example in 1D. So if we have these 5 points, we can choose k equals 2, and I'm going to randomly choose the first cluster center to be 1 and the second cluster center to be 3. Iteration 1, we're going to just go through all of the points from left to right and see which cluster they belong to. -3 is closer to mu1 than it is to mu2. And so we're going to add -3 to cluster 1. -2 is also closer to mu1 than it is to mu2, so we're going to add it to cluster 1. And now cluster 1 has -3 and -2 in it. 0 is closer to mu1 as well, and so now cluster 1 has -3, -2, and 0. And 1 is closer to mu1, so now cluster 1 has 4 points in it, and we've added 1. 3 is the final point, and it's closer to mu2, and so cluster 2 now has the point 3 in it. Now that we have our clusters created, we need to recompute our cluster centers. If we take the mean of C1, we just add up all the points and divide by the total number of points. So we do -3 minus 2 plus 0 plus 1 divided by 4 is -1. So our mean for cluster 1, our cluster center for cluster 1 is now -1. Similarly, mu2 is the sum of all the points in cluster 2 divided by the number of points in cluster 2, which is just the point 3. So we take the point 3, divide it by 1, and we get 3. So our cluster centers are now -1 and 3. We started off with 1 and 3, and now we have -1 and 3. So now we move on to the second iteration. Now we have our new cluster centers, -1 and 3, and we need to move on to iteration 2. Now we're comparing -3 with -1 and 3, and we find that -3 is closer to mu1 than it is to mu2, so we're going to add it to cluster 1. -2 is closer to mu1 than it is to mu2, and so we're going to add that to cluster 1 as well. 0 is also closer to mu1 than it is to mu2, so we're going to add that to cluster 1. And then we get to the point 1, which is equally close to mu1 and mu2. And so what we can do here is randomly choose a cluster for it to belong to, okay? I have randomly chosen to add it to cluster 1. You could also randomly add it to cluster 2, and you would get different results. So adding it to cluster 1 gives us this cluster here, which is -3, -2, 0, and 1. And then finally we check 3, and 3 is closer to mu2 than it is to mu1, so cluster 2 now has the number 3 in it. Okay, so now we have to recompute our cluster centers. If we recompute the mean, we see that we get the exact same value because we have the exact same cluster that we did last time. And if we recompute mu2, we get the exact same thing we had last time because our cluster is the exact same. So how do we know when we're done? Well, when the cluster centers don't change for 2 iterations. So we're done. The cluster centers didn't change from one iteration to the next, and so we have converged, and our answer is -1 and 3. If we had decided to add this 1 to cluster 2 instead of cluster 1, then this would continue on. But it doesn't. I leave that as an exercise if you want to work through that. Let's do a 2D example now. We have 6 points here in 2 dimensions, which means we have 2 features. And I'm going to choose k equals 2 again, and I'm going to choose mu1 to be the point 1, 2, and mu2 to be the point 3, 2. Okay, so iteration 1. We're going to start by looking at -3, 1, which is this point right here. And we're going to compute the distance between that and both of the cluster centers, which are 1, 2, and 3, 2. We're going to use Euclidean distance, remember. And what we're going to get here is 4.12 for cluster 1 and 6.08 for cluster 2. So this point right here is closer to this point than it is to this point. And visually that makes sense, and we could just eyeball it. And so we add it to C1, which is cluster 1. Now let's look at -2, -2. So -2, -2 is closer to this point than it is to this point. So again, it's added to cluster 1. Here's the actual math behind that. Now we're looking at point -1, -1, okay? This one is also closer to this point than it is to this point, and so it's closer to mu1 than to mu2, and it's added to cluster 1. And then we have 1, 2, which is mu1, right? So it's closer to mu1 than it is to mu2. And so our cluster 1 now looks like this. Okay, it has all of these points in it. From the plot, we can see that 2, 3, this point right here, this blue point right here, is equally close to mu1 and to mu2. So we randomly assign it to C2, right? So C2 has both mu2, right? We don't even need to check this one because it's the exact same as the cluster center, and this point here. All right, so now we have our clusters. We need to recalculate our cluster centers. We do this by adding all the points together in a cluster and then dividing by the number of points in that cluster. And so our new mu1 is negative 1.250, and our new mu2 is 2.5, 2.5. I have plotted the new cluster centers using these stars so we can visualize them. I have the red star as mu2 and the blue star as mu1. Now let's get started on iteration 2. What we're going to do is we're actually going to look at each point and visually compare them to the cluster centers so that we don't actually have to do all the math. But if you do all the math, you'll find that you get the exact same result. So by looking at all of these points, we can see that 3, 1 is closer to mu1 than it is to mu2. Negative 2, 2 is closer to mu1 than it is to mu2. And negative 1 is closer to mu1 than it is to mu2. That's great. So we add those to cluster 1. Then we see that 1, 2 is closer to mu2 than it is to mu1. 2, 3 is closer as well. And 3, 2 is closer to mu2 than it is to mu1. And so now we have our cluster 1 and our cluster 2. Now we're going to recompute our cluster centers. We do this again by adding up all of the points in the cluster and dividing by the number of points in the cluster. So our updated mu1 is going to be negative 2 and negative 2/3. And then our updated mu2 is going to be 2 and 2 1/3. Now we're on to iteration 3. We can see that I've updated mu2 and mu1. And so if we go through visually, we can see that the points that were in cluster 1 in the last iteration are going to be in cluster 1 again. And the points that were in cluster 2 in the last iteration are going to be in cluster 2 as well. So we can run through the algorithm again, but we'll also just realize that the clusters are not going to change. So if the clusters don't change, then the cluster centers don't change. And so the cluster centers not changing is what we need to converge. And so in this iteration, we will converge. Hooray! So that's pretty much k-means. What's great about it is that it's guaranteed to converge. No matter what starting point you give it, it will give you an answer. It won't just run forever. It may take a long time to run depending on how big your data is and how many clusters you want, but it will converge and give you an answer. It's actually a very popular unsupervised representation learning algorithm, and it's used all the time for many different things. So this starts with a fixed number of clusters, right? This is chosen by the user or the programmer. But what if we have no clue how to choose a good K, right? What if we don't even know where to start? Well, there's some other types of clustering that don't really require you to do that. So hierarchical clustering is also an iterative process, and it can be bottom up, which is called agglomerative clustering, and it can also be top down, which is called divisive or divisive clustering. So first we're going to talk about agglomerative clustering. What we're going to do for this is the algorithm, it's 4 steps, is we're going to start with each point as its own cluster. So this is going to be bottom up. We're going to start with every point represents its own cluster. We're going to identify 2 clusters that are closest together. We're going to merge those 2 clusters, and then we're going to repeat steps 2 through 3 until there's only 1 cluster. Wait, what? Right? That doesn't make any sense. Why would we have 1 cluster at the end? We're trying to cluster the data, not say, hey, here's all the data. So the result of hierarchical clustering is actually a dendrogram. So that's going to be true for agglomerative and divisive or divisive clustering. A dendrogram is just a tree that represents the hierarchy of clusters. So it represents how all the clusters were formed and combined. How do we decide which clusters are closest? How do we decide which two clusters are closest? So there's actually a couple of options here. We can use the maximum distance, which is for each point in cluster A and for each point in cluster B, you compare the distances and you use the largest of those distances. So you calculate the distance for every point in A to every point in B and you return the maximum. There's also minimum distance, which is the exact opposite of the first one, which is you calculate all the distances between points A and points in B and you return the minimum distance. And then you can also use the mean distance, which is calculate all the distances and then divide by the length of A and times the length of B. Here's kind of what it looks like. So if we had these 6 points and we wanted to cluster them using agglomerative clustering, we would end up with a dendrogram like this. So B and C are closest together, so those would get combined first and at the same time as D and E, right? So you would combine B and C, you would combine D and E, so now you have these clusters here. And then after that, you see that F is really close to D and E, and so that gets combined here to DEF. And now DEF is closest to BC, and so that gets combined, and then finally A gets combined at the end. So this right here ends up being our dendrogram, okay? And how do we actually give a clustering? Well, we just slice the dendrogram at some point, and that gives us some level of precision, whether we want really coarse clustering or really fine clustering. How do we choose where to cut off the tree? You're gonna hate this answer. It depends. It depends on what you're trying to accomplish. If you want the clusters to be really tight, then you can use that as a criteria, right? If you don't want the clusters to have a large spread, then you can use that to decide where you're going to cut the tree. If you just want to have as few clusters as possible, you can decide that. It really depends on the problem and the application. So you have to decide what's best for you for your problem domain. Okay, so now we're talking about divisive or divisive clustering, which is a top-down approach. So it's basically the exact opposite of agglomerative clustering. So we're going to start with one big cluster, which contains all the data points, and we want to split the largest cluster and then repeat this process until every point is separate. The problem with this is that there's a serious lack of detail on how to split the largest cluster. When we're talking about the agglomerative clustering, the steps are pretty clear. The only question is, how do you compute distance between two clusters? And it seems pretty obvious how to do that in a couple of ways, and I gave you a couple of examples, but exactly how you split the largest cluster is not clear. So how do we actually split the largest cluster? Well, we use something that we've already learned, k-means. So you can actually use another clustering algorithm to split the largest cluster. So you can take the largest cluster and then run k-means with k equals 2 on it, and then you suddenly have two clusters. Or some other flat clustering algorithm. So these two algorithms, agglomerative and divisive, are hierarchical clustering algorithms, right? But k-means is a flat clustering algorithm. So that's just something where the programmer chooses this hyperparameter, which is the number of clusters, and then you just run it until convergence. So those are called flat clustering algorithms. There's lots of different versions of k-means, k-medoids, and so on. So you can use any other flat clustering algorithm here to split the largest cluster. So here's the algorithm again. So we start with one cluster, which contains all data points. We split the largest cluster into two using k-means, and we repeat the second step until every point is separate. How do we choose between these two options? So they're both hierarchical. So how do we choose if we want bottom up or top down? Usually it's based on space and time. So most of the time we're going to use a top-down approach instead of a bottom-up approach, because agglomerative clustering can take O of n squared space and O of n cubed time. So typically there's a distance matrix that you use, so you don't have to continuously calculate the distance between every point in one cluster and every point in another. And so you have to keep n squared information in memory at all times. And that's not fun when you're working with large amounts of data. So typically you'll do a top-down approach rather than a bottom-up approach. Okay, so we've talked about clustering in this video, but why are we talking about clustering in a representation learning class? What is the representation that is learned? It's the clusters or the centers. So if you want to organize your data in some way, you can use a clustering algorithm to kind of suss out some information that you might not have about it, right? So you can either use the clusters to help you get more fine-grained information about the data, or you can represent the data in terms of cluster centers. So instead of having 10 million data points, you could have 10,000 data points where all of your samples are represented as 10,000, one of 10,000 cluster centers. So you can use clustering for a lot of different things, as you'll see when we talk about some of the papers for this week. All right, so for next class, which is going to be September 1st, we will actually have a class. So at 3 o'clock, there will be a Zoom session, which you need to log in for, and we will have a discussion. Okay, so there will be a quiz on clustering, which is going to be on Web Campus, and it will be available all day up until 3 o'clock on the 1st. Once you start it, you will have 20 minutes to complete it, so please do that. Just reviewing this video is enough. There's also some reading material for you if you're interested. I will post some practice problems, and you should be good to go on that. It's going to be more conceptual than working through problems, so I wouldn't worry too much about the math of it. And then we're going to review some papers that are going to be posted under week 2 on Web Campus. And I'm going to be the discussion leader for those next week, but after that, I'm not going to be leading any paper discussions. So you need to think about what topic you want to be a discussion leader for. So we're going to review at least 2 papers every week. And so I need every student to be in charge of a paper. And you need to look at the topics on the syllabus and think about what you want to be a discussion leader for. And then I will be posting papers as we go for that. So you will have time to review it and prepare. And I will make a rubric for discussion leading. But basically, I want you to learn by example. So next week, I will review a paper or 2, and I want you to kind of take notes on how I'm running the discussion, and I want you to kind of do something similar. Okay, so that's it for this, and I will see you on the 1st at 3 o'clock.